Hello, welcome to my video series of algorithms. This is part 2 of Module 2, Logic and Proof. In this video, we will discuss proposition and predicate. In our daily lives, we often use subjective language to describe our feelings and opinions. However, in the mathematical world, we need to use objective language to express concrete, factual, and unambiguous meanings. In some literature, such a language style is also called formal language. It means that the language to use should be formal. However, the term formal language usually has a different meaning in automata theory. Therefore, we will use the term objective language instead. Recall that in the previous video, we said that an argument or proof is nothing other than a list of sentences. Now that we know that the sentences included in the argument should also be objective or formal. As a result, in this video, we will discuss how to judge whether a sentence is objective and how to write objective sentences. An objective sentence should describe a fact. And since it is a fact, it should be verifiable. Intuitively, we define an objective sentence as follows. An objective sentence should describe a fact, and it must be either true or false unambiguously. Such an objective sentence is called a proposition or a statement. The validity of a proposition or statement is called its truth value. Formally speaking, the truth value of a proposition or statement must be unambiguously true or false. Another view of a proposition or statement is that it is a function that maps the real world to true or false. Here, we give some examples of a proposition or statement. For example, the Earth has more than 50% of the surface covered by the ocean. Soybeans do not contain protein. Beijing is the capital of China. All these sentences try to describe a fact, and we can determine their truth value unambiguously. As a result, they are propositions or statements. Consider some other examples. I like summer. Just do it. Can you tell me what time it is? These sentences are not declarative. They either try to express a subjective feeling, or be imperative, or interrogative. Therefore, we cannot infer any fact from these sentences. For example, we don't know whether summer is good, whether the task is done, and what is the time of the moment. Know that when defining whether a sentence is a statement, what we care about is whether it has a truth value, but not whether it is true. For example, the sentence soybeans do not contain protein is false. However, it does have an unambiguous truth value. Therefore, the sentence is a valid statement. In many cases, we use a lowercase letter to represent a single proposition or statement. For example, we can use the lowercase p to mean the statement the Earth has more than 50% of its surface covered by the ocean. And we can use the lowercase q to mean the statement soybeans do not contain protein. The inferences and reasonings that build upon propositions are classified as propositional logic. An argument or proof that consists of propositions is an example of propositional logic. While we can use propositions to express a lot of different meanings and perform many logical reasonings, there are two limitations of propositions. First, because a proposition has a fixed truth value, it is difficult to indicate the scenarios where the truth value varies depending on the actual world. For example, the sentence, Tom is a student at Kansas University, is a valid statement. This is because it tries to declare a fact, and we can verify the fact unambiguously. However, Note that the truth value of the statement may change over time. It is true during Tom's enrollment at Kansas University. It will be false after Tom graduates. Therefore, we would like to invent some way to express that some statement is factual, unambiguous, and verifiable, but still, its truth value could change. The second limitation is that it is tedious to use propositions to express existential and universal meanings. For example, if we want to express an existential statement that there exists a student wearing a red t-shirt in the classroom, we need to use the following statements. Either Amy wears a red t-shirt, or Jenny wears a red t-shirt, or Jack wears a red t-shirt, and so on. We will need to exhaust all students in the classroom. Similarly, consider a universal statement that all positive even numbers are divisible by 2. To express it using statements, we need to say the following. 2 is divisible by 2, and 4 is divisible by 2, and 6 is divisible by 2, and so on. We cannot even exhaust all positive even numbers in this case. To address these limitations, we introduce another way to construct objective sentences, the predicate, or the open statement. Recall that a proposition can be viewed as a function that maps the real world into either true or false. The predicate or open statement adopts this concept and represents a sentence as a function. The form of the statement is considered as the function, and the reality is treated as the parameters. The notation of predicate or open statement is also identical to that for function. That is, we use an uppercase letter to represent the statement form, followed by a list of parameters included in the parentheses. For example, px can be used to denote a predicate or open statement. Similar to propositional logic, the inference and reasoning built upon predicates is called predicate logic. Again, consider the statement, Tom is a student at Kansas University. We can identify the statement form of Tom is a student at some university, and the parameter will be the name of the university. In this case, we can define the predicate px as Tom is a student at X university. Of course, just like regular functions, the output of the function depends on the input. In other words, whether the predicate is true depends on what parameters it takes in. This representation thus makes it clear that the truth values of some statement forms depend on the ever-changing reality, and the truth value cannot always be viewed as a constant. Note that a predicate can take multiple parameters. For example, for the same statement, Tom is a student at Kansas University, we can also identify the statement form. Someone is a student at some university. In this case, we can define the predicate pkx to mean K is a student at X university. In short, a predicate can take an arbitrary number of parameters. Now that we have known the definition of predicates, I would like to emphasize that the ultimate goal to define proposition and predicate is to construct objective language. Therefore, we should not view proposition and predicate as different notions or concepts, but should consider them as a unified system. Specifically, there are ways that can convert a predicate into a proposition, which subsequently allows us to determine its truth value. One simple way is to specify the parameters of the predicate, in a way similar to calling a function with specific parameters. For example, consider the predicate pkx, which means K is a student at X university. In this case, when we specify the values of the parameters, such as P, Tom, Kansas, we mean Tom is a student of Kansas University. You can see that the sentence becomes a proposition, whose truth value can be determined unambiguously. Using predicates, we can also construct sentences with existential and universal meaning. To do this, we will need to introduce two quantifiers for the parameters of the predicates. First, we have the existential quantifier. When applied to a parameter of the predicate, it means that there exists an element that can make the predicate true. The symbol that represents the existential quantifier looks like a mirror flipped E. Second, we have the universal quantifier. When applied to a parameter of the predicate, it means that all elements can make the predicate true. The symbol that represents the universal quantifier is an upside-down A. When using quantifiers, we also need to specify the range or the possible set of values that the parameter can take. For example, when we say there exists an element, we also need to specify from where the element can be chosen from. The range of the possible set of values is called the domain of closure, or simply domain. We are expected to specify the domain for each quantified parameter. With the domain, the existential quantifier now means that there exists an element from the domain of the parameter that makes the predicate true. Similarly, the universal quantifier now means that all elements from the domain of the parameter can make the predicate true. In some cases, when the domain is clear in the context, we can also omit its specification. For example, when discussing numbers, we can assume that the domain is the entire set of real numbers if no specification is given. To denote a quantified predicate, we will write the quantifier, the quantified parameter, the domain, and followed by the predicate itself. For example, let Px be the predicate Tom is a student at X university. We can write there exists an X in the domain of Kansas, Florida, and California such that Px to mean the quantified predicate. Here, the mirror flipped E corresponds to an existential quantifier, followed by X, the quantified parameter. Then, we have a set that contains Kansas, Florida, and California, corresponding to the domain of X. Finally, we write the predicate itself, Px. This quantified predicate means that there exists a university that Tom is a student at. The university Tom enrolls in is either Kansas University, Florida University, or California University. Or it means Tom either enrolls in Kansas University, or Florida University, or California University. Now, after quantifying a predicate, the predicate will become a proposition. Consider the quantified predicate above, where we said Tom either enrolls in Kansas University, or Florida University, or California University. This sentence now describes a fact and can be unambiguously verified. It therefore satisfies the definition of a proposition. Specifically, we have the following rules to determine the truth value of a statement resulting from the quantified predicate. First, for an existential statement, it is true if at least one element in the domain makes the predicate true. It is false when none of the elements in the domain can make the predicate true. For example, consider the existential statement that Tom either enrolls in Kansas University, Florida University, or California University. The statement is true when Tom indeed enrolls in at least one of the universities. It is false when Tom enrolls in none of the universities. For a universal statement, it is true if all elements in the domain can make the predicate true. It is false when at least one of the elements in the domain makes the predicate false. For example, consider the universal statement that Tom enrolls in all Kansas University, Florida University, and California University. The statement is true when Tom indeed enrolls in all three universities. It is false when Tom does not enroll in any one of them. Recall that a predicate can have multiple parameters. Therefore, we can also quantify multiple parameters using multiple quantifiers. Again, consider the predicate PKX, which means K is a student at X university. We can quantify both parameters K and X. For example, we can write, for all people in the domain Tom and Jerry, there exists a university in the domain Kansas, Florida, and California, such that the person is a student at the university. We call such a combination of quantification the nested quantification. With nested quantification, we can also make a predicate into a proposition. It means that a predicate with nested quantification also has an unambiguous truth value. However, the determination of the truth values for such nested quantified predicates is a little bit more complicated. First, note that the orders of the quantified parameters do matter if they are being quantified using different quantifiers. That is, the predicate that says, for all x, there exists a y such that pxy may not express the same meaning as the predicate that says, there exists a y such that for all x, pxy. For example, consider a predicate pxy that says x plus y equals 0. The domain for both x and y are real numbers. Consider the first case, where we put the universal quantification of x first, then the existential quantification of y second. The resulting statement says that for all x, there exists a y that makes x plus y 0. This statement is true. Because for every x, we can find a y where y equals to negative x and make x plus y 0. Now, let's look at the other order, where we put the existential quantification of y first and the universal quantification of x second. The resulting statement becomes, there exists a y such that for all x, x plus y is 0. Apparently, we cannot find such a y that sums up to 0 with each of the other real numbers. Therefore, this statement is false. As a result, the order of quantification does matter. And different quantification orders may result in different meanings and different truth values. For different parameters that are quantified with the same quantifier, their orders do not matter. For example, the statement for all x, for all y, such that pxy is equivalent to the statement for all y, for all x, such that pxy. Similarly, the statement there exists an x and there exists a y, such that pxy is equivalent to the statement there exists a y and there exists an x, such that pxy. Now, we can present the rules for determining the truth values of nested quantified predicates. We first discuss the rules for nested quantified predicates with the same quantifier. Recall that for all x and for all y such that pxy, and for all y and for all x such that pxy have the same meaning. They are true when all pairs of x and y in their respective domain can make pxy true. They are false when at least one pair of x and y makes pxy false. Now, consider the nested quantified existential statements, such as there exists an x and y such that pxy, and there exists a y and x such that pxy. They are true if there exists a pair of x and y from their respective domains that makes pxy true. They're false if every pair of x and y makes pxy false. Now, let's discuss nested quantifier predicates with different quantifiers. First, look at the statement for all x, there exists a y such that pxy. It is true when for every x, there exists a y that makes pxy true. It is false when there exists an x such that no y can make pxy true. Then, let's look at the statement there exists x such that for all y, pxy is true. It is true when there exists an x such that every y can make pxy true. It is false when for every x, there exists a y that makes pxy false. For more complicated quantifier predicates with more nested layers, we can determine their truth values by recursively applying the rules above. Lastly, I would like to emphasize that objective language can be expressed in either human language or in a symbolic form. By symbolic form, we mean the use of their notations such as p, q, or pxy. Human language and symbolic form are logically equivalent. There should be an unambiguous way to translate between human language and symbolic form. Human language is easier to understand. On the other hand, the logic is more explicit in symbolic form, and its correctness is easier to verify. Finally, let's summarize this video. We focused on constructing objective sentences in this video. We presented the definition of a proposition or statement, and know that its truth value should be unambiguously determined. We further introduced predicates that can be used to enrich the expressing power of objective language. We introduced two ways to convert a predicate into a statement. The first is to specify concrete values for the parameters. The second is to quantify the parameters. We also discussed how to determine the truth values of statements. For simple statements, it should be trivial to determine their truth values. For statements constructed from predicates, we also presented rules to determine their truth values. Thank you for watching and see you next time.